Okay, hi everyone. Welcome back to class. It's Wednesday, middle of the week. Oh, post today's slide. Oh, okay, yeah, that's right. Let me do that real quick. Oh wait, delete. To trash. No wait, that's the wrong file. That's my current working slides. What you need, the pared down version. Let me upload it real quick. Yeah, because you don't need to worry about too much of the details. Here we go. Upload, continue. And oh, thank you, Lalima. That's like really great. Okay, so it should be up right now. Alright. Okay, here we go with our muscles. So, alright, big tip with studying muscular anatomy is that I will have the slides up, and with the slides, especially the Martini slides, well, the thing is that the Martini slides, if you look at if you have the Martini book and if you compare the Martini anatomy images, especially for muscular anatomy compared to the OpenStax version, the OpenStax version, I mean, it's not bad, but at the same time, I think it's like, because they use a lot of like washed out colors, I think it's a little easier to see the anatomy version of the muscles. So, spoiler, I will probably use I'll pick from the Martini slides that I upload, and I'll use those as the basis for the anatomy, not because I want you to buy the Martini book again. Martini and Pearson and Pearson and I are not on quite good speaking terms right now, but it's because I think the images are better quality, and you can also see you can see the definitions between the different muscles, and sometimes like there's a really, I mean, if you look at the overall where the picture where it shows you like all the superficial muscles of the body, it's almost like kind of like Robert Liefeld kind of cartoony bodybuilder kind of anatomy in the OpenStax version. So I think Martini shows muscular anatomy that's more, well, that's the thing with anatomy pictures. Like everybody looks like a triathlete. They have like single digit body fat. They don't have different different sizes and shapes. But I think Martini does a better job of like showing the anatomy or skeletal muscular anatomy pretty clearly. Okay, so how many muscles are there in the human body? So we know there are 206 bones, but what about like the muscles in the human body? Well, depends on who you ask. So Martini says about approximately 700, and then there's also often this number thrown around that's 640, and I'm trying to pin it down to where the original source, like it's one of those numbers that are thrown out all the time, but finding the original source that says there are 640, I had a hard time finding that, and this is the closest I could get. It was from this one, but still, it's about teaching. It's not a primary source, so I was like unable to find that. And this is actually for the professional people who study anatomies, the PhDs and whatnot. The Terminologia Anatomica, it depends. It's like 650 to 800 plus. And why do I put that asterisk? Well, it depends, like if you consider a group of muscles or a muscle group one muscle, or if you consider each different named part a single muscle, even though they all work together in a group. So there's often a debate about how many muscles are there in the human body. It's like, is a group a whole muscle, or do you consider it as individuals? In fact, I try to look in the OpenStax book to see if they have a concrete number, and they just say a large number. I mean, unless they changed it on me overnight, they don't really say a single number. So do I want you to say how much muscles are in the human body, like just a definite number? No, because again, and this is something that often you'll see in the next unit. If I notice that there's a big discrepancy and disagreement among experts about like a fact like this, then I don't test on it, because I think it's like I'm letting you know about the debate and I let you know the different responses, but I won't say that choose one of them and say this is the correct answer unless I'm able to justify it. So that won't be something I test you on. How many muscles are there? Well, we know definitely a lot more than there are bones in the body, but not a ridiculous number like 2,000 or 1 million muscles in the human body. So there are more muscles than bones. I know that's not very satisfying to some people, but that's I'm just making you aware of the debate. So with the muscular system, the anatomy, you just have to work with it, work with labeling, identifying these muscles and bones and skeletal muscular anatomy. But in terms of how muscles work, so we talked about the cellular and molecular level, but let's talk about how a whole entire muscle or muscle organ works. Now, there are these unofficial rules of the muscular system, and it's not because I'm not going to ask you like, okay, what's rule number 1 of the muscular system? No, that's kind of like trivia, like in terms of like saying what rule is what number. No. I want you to know just how muscles work in general. So this is what these rules are. So one thing is that individual muscles, if you go to the gym often, you might have if you like break up your workouts and your whole body workouts, and if you don't do a whole body, you might have to do a push day or a pull day. So you think, okay, my muscles are either pushing or pulling. But the thing is that individual muscles, they always pull, they don't push. So even though there's you might think it's a push day, it's actually your pushing movement. Even though overall movement is you're moving a load away from you and pushing it away, it's actually a series of muscles that work together, and they're all contracting and pulling on their different origins and insertions, and we'll get to that real soon. But for overall pushing movement, but if you look at them individually, they are actually pulling something. So here's an example of a simple pulling application of that first rule, that muscles pull, they do not push. So muscles attach to at least 2 sites, and these are what we call the origin and insertion. So the origin, like when you think of someone's origin or origin story, that's where they start out, right? So muscles start out at the origin, and origin or origins, because sometimes some muscles, like here we have actually the biceps brachii, it actually has 2 origins. But what are these? Are points of attachments that stay in place. So the origin doesn't move, your home doesn't move, where you start out, your hometown doesn't move. You might move from your hometown, but your origin point stays the same. Now the insertion is where another part that the muscle attaches to, and there might be multiple insertions as well, or it might not be a single point, it might be spread out. But insertion are points of attachment that moves toward the origin. So the origin stays locked in place. So remember, muscles pull, they do not push. So what's going to happen is that when this muscle contracts, this insertion is going to pull toward the origin. Or if you I know I mean, I like math, but if you've ever taken algebra or was it pre-calculus or maybe geometry into an extent, the origin with the XY axis, it starts at 0 and then it shoots out the rays to somewhere else, right? So you're always going to go back to your origin with origin insertions. So here we have an origin. So again, that's the starting out point, and it throws out that muscle toward the insertion. And what happens is that when a muscle contracts, the insertion pulls toward the origin. So again, even though we have overall movements when we're exercising that might be considered a push, it's all a series of multiple muscles working together to produce an overall movement. And these individual muscles by themselves, they always pull. So there's no way for those myosin heads to slide and lengthen a muscle actively by doing those power strokes and cross bridge cycles. It can only contract. It relaxes by undoing and releasing those tension from contraction. So again, because muscles contract, they can only pull. So have you ever tried to you can pull a rope, right? So it's easy to pull a rope, especially if you're playing certain games. So, but is it easy to take a rope and push a rope? Not really, right? So it's harder to push a rope than it is to pull a rope. So this is why muscles pull, they do not push, or individual ones. So insertions pull toward origins, not vice versa. Now, for this class, do I want you to know all of the insertions and the origins? No. So this is kind of tough because, or here's another example. So again, to have our origin insertion, so what we have is our origins up here in the scapula, and the insertions here on, here we have the radius, and I think the ulna as well. So what we have here is we're pulling the insertion toward the origin. This causes flexion when we have this with the biceps. So individual muscles, they pull, they do not push. Now, what happens if you fixate? So again, remember our origin is somewhere that's fixed, and then the insertion is something that's the muscle attaches to and pulls toward the origin. Now, most insertions are some sort of bone or bone marking. There are exceptions. An insertion might be not all insertions are necessarily a single bone, and an origin might not just be a bone either. It could be an entire structure. An example of this is the diaphragm that separates your thoracic cavity from your abdominal pelvic cavity. So the origin of the diaphragm is kind of like a sheet of muscle, but the origin is actually that part of the muscle, the perimeter of the muscle that attaches to the walls of your anterior cavity. So interesting thing is that the insertion is what we call a central tendon. So what happens is when the insertion pulls toward the origin, is that this causes your diaphragm to flatten out whenever you contract it. So most insertions are bones, but not all of them. That's an example. Okay, so the thing with origins and insertions, now we have to talk about how we move weights. And in terms, I think this is one that's not really covered in the OpenStax very well, so I will cover this very basically. And it sounds very physics-like, and does deal with physics, but what I want you to know from this class is the 3 classes of levers. So we have our first class, second class, and third class. So a load is basically a weight. So that's the very fancy term or abstract term for just some weight that's being moved. And a fulcrum is just a fancy term for a pivot or a joint. So it's something that's the central point around which this load is moving and this force is moving as well. And then you have your force or your applied force in this image right here. So basically, this is the force that's resulting from muscles contracting. So muscles are contracting, and they use a pivot or joint to move some sort of weight. That's pretty much all the muscles in your body can be applied or classified as one of these. Well, maybe for a few exceptions, but don't worry about exceptions. We're just starting out here. Okay, so first class lever is what we see here is that we see the fulcrum is between the load and the force. So think of it like a seesaw. When we have a seesaw, you have a pivot in the center between the 2 people on the seesaw. And then when you have a force, like someone's coming back down from jumping up, that's going to push the other person up, right? So the load is here we have a force, or this is a pry bar over here. This person is going to apply force on this end, pushing it down. And this load over here from the rock, this is also through gravity, trying to push it down. But by applying muscle here, you're able to lift this load. And an analogy with this in your body is your skull right here. So here we have our occipital condyles and our atlas. And so the joint between the occipital bone and our atlas is our fulcrum, our pivot. So when the muscles of the posterior neck contract, and there are many of them, don't worry about memorizing this specific list at this point. But what's going to happen is that by contracting, this shortens, as you can see here. So when it shortens, it generates force, and it's going to pull this occipital part down here and also pull up this weight. So if you just let these muscles go lax, if you just let your neck muscles go completely relaxed, your head is probably going to tip forward. I mean, it's easy for you or have you ever even watched someone during a boring lecture like this, or in the movie theater, or if you've seen them then they start to fall asleep, they kind of go like this and kind of go like that. So, I mean, when they're sleeping, they're starting to relax their muscles, and notice that their head goes forward as they're relaxing those muscles because they're no longer contracting these muscles and applying that force. So you always have that weight there, but when you're awake, you're kind of still contracting these muscles to keep your posture upright and your neck upright so your head doesn't slouch forward. Second class lever. So second class lever, instead of having the fulcrum and pivot in the middle, now we have the load in the middle. So the fulcrum is at one end and the force is at the other end, and you have the load somewhere in between. So the example they have for real life is wheelbarrow. So the wheelbarrow, the wheel, and over here is the pivot. And at the other end, when the handles, you're applying the force to lift things up. And the weight you're trying to carry is in the middle. So an example of that is your calf muscles. So your calf muscles, they're at this or not distal, but this is the posterior of your calf over here, and we have the ball of your foot that's toward the anterior. So your weight's actually distributed over your femur and tibia over here. So the weight's actually in the between the ball of your foot and the posterior of your calf over here and your calf muscles. So whenever you do go on your tippy toes, what happens is that you're moving the entire weight of your body by contracting your calf muscles, right? So the weight is actually going to go up, but it's not because the muscles are you're not contracting your anterior calf muscles, you're contracting your posterior calf muscles. So this is an example of a second class lever. Now third class lever, so most of the muscles in your body are third class levers, and you do have the pivot and fulcrum at one end, but instead of having the force on the opposite end, now the force is between the weight and the fulcrum. So what's the weight being moved here? The weight is pretty much the entire forearm over here, or anything like if say you're holding a dumbbell or something in your hand or palm. So all this weight over here is going to pivot along this joint, and you have this muscle that's moving, using or generating the force that's going to move this weight over here. So your forearm and any weight that you happen to be holding. So this is a third class lever, and here's a quick mnemonic to know these mnemonics. So okay, first one is like, how many heads do you have? You have your one skull, right? So you have your skull. That's an example of your first class lever when you're moving your neck and nodding it up and down. Second class lever, how many calves do you have? You have two calves, right? So two calves is calves are an example of a second class lever. And a third class lever, imagine you're doing a dumbbell curl with your biceps, and you're curling a 3-pound weight. So pretend you're like, I know some of you, whenever I present this in live, like some of the bros are like, oh, I can lift like 10 times or 20 times that weight. Yeah, just pretend you're just doing it for the example. You're not talking about 30 class levers. So a third class lever, just think you're curling a 3-pound weight, and then you're going to curl it with your biceps. That's an example of third class lever. Now, is there a fourth, fifth, and sixth? Well, think about it this way. So first is, again, your skull and your occipital condyles and your atlas. Second class, your calves, 2 calves. And third, that 3-pound dumbbell. Now, is there a fourth, fifth, and sixth class lever? Well, if you look at this, the way I arrange things, even if you put like force, fulcrum, and load, that's just this in the opposite way. So this is why there's only 3 classes of levers. There's no fourth, fifth, and sixth, because these are the only 3 possible ways of distributing these forces and loads and pivots in relation to each other. Other examples of muscles for each type of lever, focus on these. I think it's like, if I introduce more muscles in the next 2 lectures and mention the levers, then I think they're fair game. But start out with these and know that most of the muscles in your body are third class levers. So first and second, we have some examples, but third is the majority of them. We have the force between the fulcrum and load. So I'm not so much about, for this concept, like you memorize this muscle is this type of lever, but do you know how the force, the fulcrum, and the load are arranged in relation to each other in the first, second, and third class? So again, first is that seesaw, second is the wheelbarrow, third is like that slingshot. Okay, so what we have here is, okay, so in the previous 2 lectures we focused most on the myofiber and myofibrils. Now let's focus more on the fascicles. And so this is between like the whole muscle organ and the cellular and molecular level. Now there are different types of shapes and fibers. So what we have are like not all, even though they all contract, they're all excitable cells, they're all muscle tissue. They have different shapes, like the muscles in over here with their orbicularis oris surrounding your lips. It's not the same shape as your pec major, not the same shape as your sartorius or your deltoid. Now circular muscles, what happens when they're relaxed? Well, again, when a muscle contracts due to sarcomeric shortening, it's going to shrink, right? So if you have a muscle that's round like this, what happens if you shorten it and decrease its circumference? Well, it's going to shrink like this. So this is what happens with circular muscles. When you contract them, that ring draws tighter. So it's like Or if you have like a drawstring pouch, I don't have one right here, but or like a drawstring bag, like those are really popular at the gym. When you pull that drawstring and draw it, contract it, and kind of bunch it up, what happens to that opening? It starts to get smaller and smaller and smaller. Same with the circular muscle. Also, the sphincters of your body, they often have these circular muscles. That's why they're sometimes also called sphincters. So example of this, the orbicularis oris that surrounds your mouth. And this is about, yeah, so they're also known as sphincters in multiple places in your body. Now, parallel muscles, well, back to high school geometry, when you have two parallel lines, they don't intersect, right? They're just along each other. So if these are like parallel lines, they're all aligned with each other, right? Same with the fascicles and parallel muscles. They don't weave into each other and intersect. They're all side by side by side. But what we have here is cross section. So if you look at all of these fascicles over here, they're all going to be parallel and not weave among each other. And here we have a fusiform parallel. So they're parallel, but they start off somewhere and they're all parallel here, but they taper off at both ends. So that's what we have here with the fusiform parallel muscle. So example of this are your bicep brachii and your upper arm. And the rectus, so your abs, your rectus abdominis, this is another example of a parallel muscle, but non-fusiform. So it does kind of taper off here at the end, but not like your biceps. So notice that all these fascicles over here, they're running parallel over here. And this is why they're kind of like a broad sheet rather than bulging out in the center like here. So rectus abdominis. And your supinator. So remember, like when you're trying to remember pronate and then supinate. So your supinator that helps with supination is another example of parallel muscle. And it wraps around, because if you look at the supinator, it has kind of actually arranged around like this. So what happens is it kind of wraps around the radius and ulna to help with the action of supination. Now convergent muscles, notice that it's kind of parallelish, but it starts out wide and then tapers off at a point. So another thing that they might say is that it's kind of fan-shaped. And an example of this is your pec majors, and here we have the base of the muscle, and this is actually toward the sternum. Over here, and your midline, and then it inserts here on your shoulder. So this is a tendon, so it starts out wide and then converges on this tendon right here. And then, so what happens when the pec major contracts? So this tendon is actually the insertion, and this entire base is the origin. So it's going to pull this way and draw the shoulder toward the midline. And then pennate muscles. So pennate refers to, like, I think if I remember correctly, the etymological origin refers to a feather. So this is what a unipennate muscle looks like. It looks like a single quill or a feather. And here's the extensor digitorum, and what we have here is a tendon that's extended. But all the fascicles, they're arranged this way. So when these fascicles contract, because fascicles, again, are made out of individual myofibers which contract due to sarcomeric shortening. So when these contract and shorten, they're going to pull the tendon along with it. So this is, why is it unipennate? Well, it's only on one side of this tendon. Now I'm saying unipennate because there's something called bipennate. So bipennate, so bi means two, right? Like a unicycle has one wheel, a bicycle has two wheels. With a bipennate muscle, what we have is a central tendon over here, and then we have a rectus, so example is a rectus femoris. And all the fascicles, they're arranged this way, and when they contract, they're going to pull toward this central tendon and pull the rest of generate this overall upward movement if you're talking about anatomical position. Now multipennate, compared to having things or just like Squid Game, right? So what happened was, like, remember the winning team, spoiler, was that during the tug of war, what's one of the winning strategies? You stack your people on both sides rather than all on one side, right? So that's what bipennate is, kind of like you're stacking your forces on both sides of a central tendon versus just one side. Now multipennate, what happens is that even though it looks deceptively simple over here, you actually have multiple fascicles and multiple central tendons. So this is a cross section of the deltoid, And we have these central tendons in the middle of all these fascicles that surround it. So if we looked at the individual fascicles and how they contract, it would be something like this. So the deltoid is actually very complex in terms of how its fascicles are arranged, but it generates a lot of force that pulls that insertion towards its origin over here. So all these fascicles, they have an overall direction they work toward, but if you look at them individually, they have different arrangements. And another thing is like, okay, how do I tell the difference between parallel and convergent and pennate? Well, look how the fascicles are arranged and how the overall direction of movement, how the fascicles are arranged and the overall direction of the movement. So here we have the rectus abdominis, the abs, and the parallel fascicle arrangement. So when you contract your rectus abdominis, it's going to contract this way. Well, same with these like parallel muscle fibers. When they contract, it's going to pull this way. So notice that the parallel muscle fibers, or the fascicles, they're arranged parallel to the overall direction of movement. Now with convergent, this is the way the pec major contracts, but how are the fascicles arranged? They're not arranged parallel to the overall direction of movement. They're actually fanned out. So these up here, they're actually pulling slightly off. And maybe this one right here is parallel, and you have some that are pulling in the opposite direction but at an angle, but the overall movement is going to go toward the midline. So this is one with convergent. Notice that these fascicles, they're kind of fanning out from this insertion. And then with pennate, what we have is an overall direction of movement, but again, unlike the parallel fascicles, we notice that they're kind of like a herringbone or fishbone compared to the overall direction of movement we see with this dark red and purple arrow. Notice that the fascicles are arranged like this, but it's not fanning out like a convergent muscle over here. It's kind of being kind of like ranged, kind of like at an angle, at a skew to the overall direction of movement. And another way you can tell the difference is take a cross section. So notice that fascicles do not intersect in the parallel muscle because, again, parallel lines do not intersect. Neither do the fascicles of a parallel muscle. Convergent, well, it depends where you get the cross section, but notice that they all kind of like taper off at one point and then they spread out. And then with the pennate, especially with the multi-pennate, so if it has more than like bipennate, it's considered a multi-pennate, is that we have these central tendons that you don't quite see in the parallel or convergent muscles. So even though they all contract, they're just arranged differently. They do have origin insertion, but the fascicle arrangement can differ between different muscles. And focus more on the examples I give here and recognizing the different types of fascicle arrangement. Alright, so another unofficial rule. So basically it's kind of like for every action there's an equal and opposite reaction, but this is talking about muscles. So say you're like floating in, or you're on the ground where you're not fighting gravity and you're in an anatomical position. If you do a joint movement using a muscle, then there are muscles that undo that joint movement. So if muscle does an action, there are muscles that oppose that action. And here's an example of that. Here we have our humeral ulnar joint, our elbow joint. And how do we do flexion? Well, we're going to contract these muscles over here. So here's the elbow joint. And when we do flexion, we're going to decrease the angle between our upper arm and our forearm, right? So we're going to do this by contracting this muscle, and this muscle, when it contracts, is going to bring the forearm and the hand and any weight that the hand happens to be holding toward the shoulder. And so these are flexors because they assist with the action of flexion or at the elbow joint. Now on the opposite side, we have something that extends. So what happens is that, can we extend by contracting these muscles that are in the front? No, right? Because it doesn't make sense, because if you contract this muscle, then this would just decrease the angle even more and more and more. So what you want to do is contract these muscles over here on the opposite side that are going to extend and pull this part of the ulna toward here, thus extending the overall elbow joint and causing extension. So this is why these are called extensors of the elbow in the posterior of the upper arm. And over here is that we have abduction and adduction. So here we have an abductor group, and there's many of them, but let's talk about this joint over here. So remember, abduction is moving away from the midline, adduction is toward the midline. So when we have abduction, we're going to move this femur, this upper leg and thigh, away from the midline. And this is what we have here. So this group of muscles here collectively that are attaching to the and wrapping around the greater trochanter, these are abductors. And on the opposite side, come on PowerPoint, come through. Let's see. Sorry, PowerPoint froze for a bit. Okay, so here we have abductors over here. And adductions, notice that they're going to move in the opposite direction, right? So abduction is away from the midline, adduction is toward the midline. So adduction is going to involve these groups of muscles that are going to contract, and by contracting, they're going to move this femur closer toward the midline. So what do we notice about these examples? Notice that muscles that oppose each other, they tend to be located on opposite sides of the body. So just like we have our flexors of the elbow toward the anterior of our arm and our extensors of the elbow toward the posterior, same with the abductors and the adductors. The abductors are more located lateral at the hip, and the adductors are located medial at the hip. So this is so now we have to also talk about these other vocab words. So what we use so movements are complex. Like even like simple gym exercises, they can be broken down into a series of joint movements, and even just saying which ones or what muscles are driving those movements is actually a pretty involved science. But so now we have to use these terms to describe the importance and the roles of a muscle in an overall movement. So there's something called the prime mover or agonist. Depending on your textbook, I think you should know both terms. But when you have a prime mover or agonist, this is the main driver. So this is why it's prime. It's primary. It's first. An agonist, and this is kind of a useful term to know, it's something that does something. So it's a main driver behind a joint movement when we're talking about skeletal muscular movements. And then an antagonist, so it's just like the antagonist in a story where you have an antagonist in a story, they're going to oppose someone, right? So this is what we call with the antagonist muscle. If you have a muscle that does a movement and the muscle that undoes the movement, the muscle that undoes the movement, the one that opposes the movement, is going to be called the antagonist. Just like an antagonist opposes a protagonist. And that's a common misconception. So sometimes people think like, oh, it's a prime mover and a protagonist. And unfortunately, that doesn't apply to muscle movement. It's agonist and antagonist. And I like to think this way. So here we have, and if you've seen this movie, I'm putting this smiley here so that the mouse doesn't get upset and to copyright strike my stuff because I'm using their characters. But here we have Mr. Norse God, and he's the prime mover, he's the agonist of the story. So he's again, there's no such thing as a protagonist in joint movements, but he's the one that starts off the movement. And who's the antagonist? Well, it's antagonist lady over here. So antagonist lady is trying to oppose and undo everything he's trying to accomplish. Now synergists. So synergists are muscles that help the prime mover, but they're not the main force behind the overall joint movement. So what I like to think of it as synergists, to use this kind of like this play and storyline analogy, is like synergists are things that are muscles that help the prime mover, help toward the goal, but they're not the actual prime mover themselves. So they're not the main feature of that movement. And then there's another term called fixators. So these are muscles that help with stabilizing the movement. So they actually don't contribute to the overall movement in terms of like directly the actual like joint movement, but by contracting and helping to stabilize the joint, they and other muscles, they help with overall movement. So they're kind of like side characters, yeah. So this is what I like to think of fixators. They're the NPCs. They kind of help with stabilizing the movement, but do you necessarily need them to move along that movement? Just like, do you necessarily need these? They contribute a lot, but are they completely necessary? Not so. So you have, again, your prime mover agonists, your synergists, your antagonists, and fixators that are kind of helping along, but they're not quite as important as, or I shouldn't say they're not as important, but they don't help directly with that movement. They're kind of there in the background and helping out in their own little way. Alright, so fixators, they help to stabilize movements. And why is it important to stabilize a movement? Well, it helps to make a movement more efficient because you can still do a movement without fixators, but might require more energy. So what if you didn't have fixators? Well, if you've ever done this, like especially in elementary school when you're starting to do PE, what do you have? You have your buddy or someone just pair up, someone supports your ankles, and you do sit-ups this way. So this is like so what's happening? This buddy is kind of working like a fixator. So by helping to anchor you, it helps make your sit-up easier. But what happens when you don't have someone holding your ankles? Can you still do a sit-up? Yeah, you can still do a sit-up, but with if you don't work out a lot and do a lot of ab movements, it's a lot harder to do it without someone fixating you, and if you're just trying to do this with just planting your feet on the ground. Or if you're doing like another abdominal crunch, but you have your legs off the ground, without the additional stability by having your legs or your feet fixated on the ground, it's a lot harder to do that, crunch that same rectus abdominal muscles. So fixators, they provide additional stability to make the overall movement easier and more efficient. Yep. So this is we didn't have fixators. Yeah, so this is why fixators help to make a movement overall more efficient. And what if you didn't have fixators? Well, here's an example. So here we have a movement.
The idea is that you're going to be reaching down to lower your center of gravity, and then just by natural gravity let your legs fall and then flip over.
So this guy's flipping over, and what's happening as he's flipping over? He's engaging many muscles, and including his core, to help with the overall movement so that he does a quick parkour and efficient flip.
Your center of gravity, and then just...
Now, what if we didn't have fixators and we were just trying to get ourselves over a bar? It might look something like this. So same movement, but is he engaging his core? Is he engaging his fixators? He's using muscles and he's getting over the bar, but look at the loose movement. And yes, if this looks very familiar to you, if you live in the Haleoha Towers, you know where this is. But yeah, so fixators are important for efficient movement. You can still get the movement done without fixators, but by bringing fixators into the picture, that makes things a lot more efficient. Now, with actions and movements, so things that we can describe simple movements, and I'm not going to go over very complex actions and movements in this class. I'll save that for your kinesiology classes. And what we have starting here and then going over here, do we have shoulder abduction or adduction? Actually, don't want to boot up top hat. Okay, what was that? Abduction, adduction. So starting from here and going here. So start, finish. Oh, I don't have my water. And if we didn't have fixators, we'd end up with a terrible movie. Yep, so fixators, even though they're not the prime movers or synergists, they help. And let's see. So most of you are saying abduction, and most of you are correct. That is shoulder abduction. So we're moving the upper limb at the shoulder, and we're doing abduction because we're going away from the midline. So what's the prime mover and agonist? Well, it's the deltoids over here. So this guy's deltoids, when they're contracting, they're helping to move his upper limbs at the shoulder, and they're bringing it closer toward toward his neck and over here. So they're moving it away from the midline. Now, what are the antagonists? Well, they're going to be basically things that move his upper arm back toward the midline. So in the front, we have our pec major. Our pec major starts out here and inserts over here. So if he contracted his pec major, it would move his arm back toward the midline. The lats or latissimus dorsi. So the latissimus dorsi is actually in the back. We can't see it too much from here, but it's going to also pull this arm from the posterior back toward the midline. So this is why we have the antagonists. Now, synergists, we have our supraspinatus, and hey, supraspinatus, remember our spinous process of our scapula, and the supraspinatus is above that. So when that contracts, that's going to help along. So it's not going to be as powerful as the deltoids, but it's on the back of the shoulder over here, and it's going to help to pull that shoulder and pull that upper arm away from the midline. And the fixators, now this is where things get kind of complicated. There's often many fixators for even a simple joint movement. And example are like the rhomboids in the back posterior muscles. Now over here, what is she doing over in this? Now compared to shoulder abduction, now we're going to have shoulder adduction. So this is where you have to be very careful, because notice that these two terms, again, differ just by one letter. So shoulder adduction, she's adding things toward her midline. So she's starting off here, ending here. Now what are the prime movers? Our pec major and lat dorsi in the back. So here we have a pec major in front, lat dorsi in the back. And our antagonist is going to be the deltoid. And hey, that was our previous protagonist, right? So because why? Well, the deltoid contracts is going to move her arm away from the midline. And synergists, we have our infraspinatus and teres minor. Hey, two more rotator cuff muscles. And our fixators are also our infraspinatus and teres minor. So this is where things get kind of interesting. But what did you notice between shoulder abduction and shoulder adduction? Well, notice that with shoulder abduction and shoulder adduction, our prime mover in abduction were our deltoids. Now our antagonists, they were our pec major and latissimus dorsi. Now with shoulder adduction, what was our prime movers? Our prime movers were actually the pec major and latissimus dorsi, and our antagonist was the deltoids. So they did a switcheroo between two opposite movements. So notice that this is what a trend you often see with direct opposite movements. The prime mover in one movement, when you have the opposite movement, is going to become the antagonist, and vice versa. So this goes hand in hand with that unofficial rule number 2, right? So if there's a muscle that does an action, there are muscles that oppose it, but this goes hand in hand with the whole definition behind a prime mover and an antagonist. And here we have another deceptively simple movement. And what are the prime movers over here? Well, basically your anterior for our upper arm muscles. So here we have elbow flexion, because again we're decreasing the angle between the upper arm and the forearms. And then what we have here, so prime mover or agonist, is it the brachialis or biceps brachii? And this is why I put a little asterisk, because I've seen multiple resources saying either way, so do not worry. Again, I can see the case for either one, but am I going to get into the argument of taking a side of the brachialis or biceps brachii? I'll leave that for the ortho bros and the kinesiology majors and professors, because I'm like, okay, but I've heard like things like it also depends on your position of your forearm. The strongest argument I heard for the brachialis is like that's the one that attaches to your ulna, and that remains constant and that remains engaged no matter which way your forearm is positioned, whether it's supinated like this with your thumbs up or in the middle, or is it pronated. So that's why, like, if you've ever done like biceps curls or if you've done arm curls in the gym, it does feel different unless you're very just muscular overall and very well balanced. Try to lift a dumbbell with your arm supinated and your dumbbell with your arm pronated. I'm like really weak when I try to do it pronated and compared to when I do it supinated, and there is a difference. But again, that's a little advanced for this class. Don't worry about for one, or maybe in more advanced like upper limb classes you might have to worry about that. The antagonists, again, just like we have muscles that oppose each action, notice that this is on the opposite side. So instead of being on the anterior of the upper arm like the brachialis and biceps brachii, the triceps brachii is on the posterior. And the synergists, again, depending on the textbook, if they say that the prime mover is the brachialis, they say the biceps is the synergist. If they say the biceps is the prime mover, they say the brachialis is the synergist. Again, I'm going to get into that debate, not in this class. And fixators, rhomboid major, among many. So there's actually, if you look up a joint movement and the prime mover, antagonist, synergist, and fixators, there are laundry lists. So resources sometimes differ, and this is what I'm getting at, is like when there's a debate, I let you know about the debate, but I don't really like say this is canon because sometimes it's really hard to tell. For the lab, if you're doing actions and movements, I told the TAs to be very specific about their primary sources. So if they choose a primary source, go with that for your lab section. But this is why I don't really teach it at this level, because there are the things that if you look at just even a simple joint movement, sometimes there can be like a handful of synergists, maybe one synergist. There might be like up to 5 synergists, and fixators. Sometimes it can be a dozen fixators for just a simple joint movement. So this is why I don't expect you to memorize lists of synergists and fixators and prime movers and antagonists. But what I think you should definitely be able to do is be able to define these terms. What's a prime mover? What's an antagonist? What's a synergist? What's a fixator? So you should be able to define these in terms of muscles and joint movements. And I like to think of it, and what's a practical application of this? Like when I used to go to the gym more often, I noticed that like one of my weak points and one I would always wish would grow bigger were my delts. But I noticed that like with I tried to do a lot of shoulder presses, but my delts wouldn't really grow a lot. But I noticed that if I tried to do it in the mirror, like when I did a shoulder press, I noticed my upper pec would always like contract. And my friend who's a physical therapist, he said like, well, why don't you try contracting your lats and contracting your rear shoulder blade muscles and your rotator cuff to fixate your scapula, and then try to do your shoulder presses. And the whole logic behind that is like by engaging my lats, well, that's opposing the action of my up pecs over here. So that would prevent my pecs from contracting because I'm trying to focus on my back. So he was saying like maybe you should fixate your posterior chain muscles in the back of your body and try to, while doing that, then you do your shoulder press. So I was actually making gains and then COVID hit. But this is how you're able to, a practical example of how you're able to use agonists and antagonists. It's very hard to engage both at the same time unless you're using an isometric exercise. But by doing that, he was able to kind of trick my body into not engaging my upper pecs as much during a shoulder press and taking the brunt of the load and force compared to my delts. So by taking my pec major out of the equation, I was able to use my delts more, engage them more during a movement. So yeah, that's a practical example of like, especially if you're into exercise, of using prime movers and antagonists. And we're out of time, so I don't really have time to cover skeletal muscles. I've got to double check if these are up. But yeah, there are a lot of superficial muscles over here, but I think, so here's what's going to happen. Here we have overviews of the muscles. I think this is also in the slides I uploaded as well. And here's, again, the cartoony, yeah, look at these tiny, tiny feet compared to the rest of the body. I think that's hilarious. So notice the proportions in the OpenStax version. They're kind of interesting compared to the very thick body, very tiny feet. I think they're trying to illustrate the muscles, but yeah, it's kind of interesting proportions. And over here, it's like super big trunk and super thick legs from the back. It looks like almost like they skipped leg day, right? Of course, there's a lot of cut muscles. So this is why I will borrow from the Martini version for muscular anatomy, because I think it's a lot clearer and easier to see compared to the OpenStax version, which is kind of cartoony in parts. So yeah, it's free, but we get what we pay for. Now, why do I cover this? Like, all of these muscles that are in these slides are fair game. So they can show up on the test. And let's see, so be able to identify and name all of these, and including pictures showing regions up close. Let me edit this slide and put this on the back. Yeah, so I want you to at least, like, if you haven't started on your skeletal muscular anatomy, start off with these 4 images sent to back. So start off with these 4 images and including the picture showing these regions up close. So why will I zoom in on pictures? Well, it's very hard to identify these muscles over here when they're very small. So sometimes I will zoom into a region, not to make it more difficult, but so you're able to see a muscle more clearly. And at least for the muscle anatomy questions, at least 50% will be based on the muscles that are listed in these 4 images. So not necessarily from these exact images, but because it could be, I could show up you a close-up of the arm rather than showing the, okay, can you point out the brachioradialis in this overview here? I probably will show you up close of the arm if I'm trying to show you a smaller muscle. So look at the Martini slides, and the remainder muscles will be listed on the study guide. Spelling count, again, unless you're taking the makeup exam, spelling is all multiple choice. But again, spelling does count. Like if you say like, oh, I chose abduction but I meant adduction, no excuse, there's a difference. So course guide isn't. So course guide will be released on Friday. That guy is built like Gru. Yeah, that's right. Big body, small limbs. Especially over here, he looks like Gru from the back and degloved. But yeah, so again, spelling does count, especially for adduction and abduction. Oh, those are like very close in spelling. But again, if you're taking the regularly scheduled exam next week Friday, it's about recognizing the spelling. You're not spelling it itself. Bamboozle with misspelling? No. Again, it's like spell check, and if it do misspell something, then and it ends up as a different term, I give that's a mea culpa on my part. But no, yeah, I'm not gonna purposely misspell stuff. But again, this stuff is already hard enough as is. So this is why you should definitely be careful, especially with abduction versus adduction, because so close together, just differing by one letter that can be flipped around. So, or teres major, teres minor. Again, a lot of these terms can be very similar in their name, but again, they are different if they're, or like for the lab, the general rule is like if you misspell something but it spells something totally different and a different structure that's the correct spelling of another structure, yeah, you don't get the free pass on that. Clarify majority is picture based and multiple choice. So again, it will be multiple choice for the regular exam, and picture based, it's about like, well, not all of it, but if it's anatomy based, like the chapter 11 or chapter 7 and 8, you'll expect more pictures than you will text based questions. So not all of it will be picture based, but like skeletal tissue and muscle tissue, maybe not so many pictures, but definitely for muscular anatomy in chapter 11, it'll be mostly picture based. All right, so we're definitely over time, so I'll see you all on Friday. And oh yeah, thanks again for tuning in, and thanks to our moderators.